All right, today we are diving into something really cool. A revolutionary tool that lets us peek into the very building blocks of matter. It's called density functional theory, but you can think of it as a kind of quantum shortcut. And believe me, it is changing everything. So, how can we do something like design a brand new solar panel or even a better drug entirely on a computer? I mean, it sounds like something out of a sci fi movie, right? But it's not. The power to predict how material will behave before you even make it is totally real. And this quantum shortcut we're talking about, it's the engine making it all happen. So let's break down how it actually works. Okay, so to really get why this shortcut was such a game changer, you've got to understand the massive, massive puzzle scientists were up against. It all starts with electrons. You know, these tiny particles buzzing around inside every atom and molecule. The challenge was, how in the world do you describe what all of them are doing at once? Well, it turns out there's a rule book for the quantum world. It's called the Schrödinger equation, and on paper, it's the master key. If you can solve this equation for a system, you can predict, well, pretty much everything about it. Sounds great, right? But, oh, there is a huge catch. It works beautifully for something simple, like a single hydrogen atom, but for anything more complex, the equation turns into an absolute monster. And this is where the problem just explodes. The complexity doesn't just add up, it multiplies like crazy. See, every single electron you add brings in 3 new dimensions to the problem. So let's say you have a tiny molecule with just 10 electrons. You're no longer trying to solve a puzzle in our normal 3D world. Nope. You're trying to solve it in 30 dimensions. Think about that. It's not just hard, it's fundamentally impossible for our best computers to handle for any real-world material. All right, so the direct path is a total dead end. It's blocked. So what do? Well, scientists had to get really, really clever. They started searching for workarounds, for approximations, basically ways to simplify the problem just enough so they could get a useful answer without getting totally lost in that impossible math. And the years right after Schrödinger's equation came out were just buzzing with these brilliant new ideas. First, you had the Born-Oppenheimer approximation, which basically said, hey, the nuclei are super heavy and slow, let's just pretend they're standing still. That was a huge help. Then you had guys like Hartree, and later Hartree and Fock, who started to tackle the real beast, how all those zippy little electrons are interacting with each other. So the big idea behind these first attempts was something called the mean field approximation. And it's a pretty smart idea, actually. Instead of trying to track the push and pull between every single electron and every other electron, which is just madness, it simplifies things. It says, let's imagine that each electron is just moving through this kind of averaged out, blurry cloud of all the others. The crowd analogy is perfect. You're not reacting to the guy 3 rows back. You're just reacting to the general vibe of the crowd around you. Same idea. Now, the Hartree-Fock method was a huge leap forward. It was much more sophisticated. It brought in some really important quantum rules, like how 2 electrons can't occupy the exact same state, and it got so much closer to the real answer. But it wasn't perfect. It still missed a crucial little piece of the puzzle called correlation energy. You can think of this as the complex little dance the electrons do to actively swerve and avoid each other. The mean field idea was good, but in reality, electrons are a little bit smarter and more coordinated than just moving through a blurry cloud. So these mean field methods, they were getting better and better, but they were all still trying to climb the same impossible mountain. They were just finding slightly better paths. What science really needed wasn't a better climbing technique. It was a tunnel, a way to go straight through the mountain and ignore the climb altogether. It was time for a revolutionary shortcut. And this is where the hero of our story enters the picture. It's called electron density. The big idea, the revolutionary idea, was this. What if we just stop trying to track every single individual electron? It's impossible. Instead of watching the chaotic swarm of a million bees, what if we just made a simple map of the shape of the swarm? You know, a map that just shows where the bees are most concentrated. That simple 3D map, that's the electron density. And that shift in thinking, that is the absolute heart of density functional theory. This is the big aha moment. We go from wrestling with this nightmarish, multidimensional thing called a wave function in 30, 60, even hundreds of dimensions, to dealing with something that always lives in our familiar 3 dimensions. It's just a 3D map. The complexity problem wasn't just made easier, it was basically erased. A total game changer. Now, you might be thinking, okay, that sounds neat, but does it actually work? Well, in 1964, two physicists named Honenberg and Kohn came along and proved, mathematically, that it's rock solid. Their first big theorem basically says that this simple 3D electron density map, it contains all the information you need. And their second theorem gives us the recipe. It says the true correct electron density is the one that minimizes the total energy of the system. So they didn't just give us a cool idea, they gave us the rule book for how to use it. So the theory is beautiful, it's elegant. But a theory on a blackboard doesn't help you design a new battery, right? The next crucial step was figuring out how to turn this brilliant idea into a practical tool that scientists could actually use on a computer. And this is where the rubber meets the road. It's called the Kohn-Sham method, and it's basically a really smart feedback loop. Here's how it works. First, the computer makes an educated guess of what the electron density looks like. Then, it calculates the forces, the potential that this density would create. Step 3, it solves for where the electrons would actually go in that potential, which gives it a new, better electron density. Then, the final step, it compares the new density to the old one. Are they the same? If yes, boom, you found the answer. If not, no problem. It just takes that new density, uses it as the next guess, and runs the whole loop again, getting closer and closer to the truth with every single cycle. Okay, there's just one last little detail. Remember that correlation energy we talked about? That complex little dance the electrons do? Well, it's still in here, but we don't have a perfect mathematical formula for it, so we have to use clever approximations. The two most common flavors are called LDA and GGA. You can think of LDA as the simple version. It treats the electron density like a calm, uniform sea. GGA is a bit smarter. It looks at the sea, but it also pays attention to the slope of the waves, how fast the density is changing. Scientists just pick the best approximation for the problem they're trying to solve. All right, so we've been through a lot of theory. The big question is, what's the payoff? Why does any of this actually matter in the real world? Well, the answer is, it matters everywhere. DFT isn't just a cool idea. It has become one of the absolute workhorses of modern science. Using DFT, we can now calculate the fundamental properties of a material from the ground up, just using the laws of quantum mechanics. We can ask the computer, will this material conduct electricity? How strong is it? How will it react to light? And getting the answers to those questions is exactly what you need to design things like better batteries, more efficient solar panels, stronger airplane parts, and even brand new medicines. And I want to be clear, this isn't some obscure theory that only a few people use. It's the literal engine running inside these huge, powerful software codes that you see here. Programs like Quantum Espresso and VASP are used every single day by tens of thousands of scientists and engineers all over the globe. DFT is a true cornerstone of computational science. This quote really just says it all, doesn't it? The main objective is to replace the many-particle wave function with the electron density. That was the revolution. It was about changing the main character of the story. By shifting the spotlight away from that impossibly complex wave function and onto the beautifully simple electron density, DFT handed scientists the key to the quantum world. So that brings us to today, and to the future. We now have this incredibly powerful quantum shortcut that lets us design materials from the atoms up. I mean, the possibilities are just staggering. Think about designing new materials to pull carbon right out of the air, or creating the building blocks for the next generation of quantum computers. The quest that started almost a century ago is still going. And it leaves us with one really exciting question. What problem